Okay, part two of our intro to waves. We're finally, so far we just really talked about vibrating objects. Now we're finally going to get to actually talking about what a wave is. I've typed it up in with the idea of an activity. What I'd like you to try and do is get some water that you can play with. Like if you've got a baking dish, like a 9 by 13 that maybe you make birthday cake in, that would work. If you have access to like a big Rubbermaid container, you could put a bit of water in one of those. If nothing else, you could try putting a bit of water in your bathtub. If you're lucky and can safely access a swimming pool, you could even try it in a swimming pool. If worse comes to worse, read through all this stuff and just kind of use your imagination. I've looked for online simulations, but I couldn't find any that were simple enough. So the ones that were out there were kind of crazy simulations of this. So here we go. Hopefully you've tracked down, pause the video if you need to, but hopefully you've got something that you can put water in the bottom of and play with this little experiment. The goal of this is like, let's say instead of doing it this way, I just asked you to find the definition of a wave. If you went and Googled it, you're going to find it's going to say a wave is something to do with a disturbance and energy and propagation and medium. All these weird physics words would be in the Google answer of what a wave is. But you've already got some common sense and some experience with waves. So what we're going to do here is I'm going to try and connect your good common sense with sort of the physics vocabulary and concepts that are already in your brain. Take your time and go through here, but if we work through well, then those good concepts that are in your brain, we're just going to add physics vocabulary and understanding to it, so we can deepen your pool of knowledge of waves. I was pretty excited when I typed that. All right, here we go. So if you haven't done it, go get a body of water, and we're going to let it rip. If for some reason you can't do it, I do have a video clip of when I try to do it down here. It is a little bit messy, but give it a whirl. Okay, the physics of this rather simple experiment. Vibrations are always something elastic, something that wants to get back to its preferred position. If we think about your little body of water, gravity is kind of the driving force, and it wants that body of water to be perfectly horizontal or flat. So in a way, kind of like the hanging ruler, if the water ever gets disturbed and isn't perfectly flat, then it tries to get back to that preferred position, which means we can call it elastic. When you tap the water at a particular location, so near one end, let's say, you made the water at that location start to vibrate. If we just watched that point where you're tapping it, the water would be wobbling, vibrating up and down, just like the end of the ruler wobbled up and down. It's all going to kind of work through here, but just like the ruler activity, if you tapped with more energy, the amplitude would be bigger. If you somehow change the physical properties of your body of water, the easiest way would be add more water or take water away. That would change the physical properties. That would change the frequency. Still, that little paragraph I just highlighted, we're still talking about vibrations. Now here's what a wave is. When you tap the water at a particular location, you made the water at that location start to vibrate. So right where your finger was, that water started wobbling up and down. That up and down wobble triggered the water right next to it or adjacent to it to also start to wobble. So if you touched the body of water kind of at one end, the water right under your finger was forced to wobble up and down. But that made the water right beside where you were touching wobble up and down. And that water that started wobbling up and down, that triggered water a little bit farther away to start wobbling up and down. And that wobbling water triggered water even a little bit farther away to start vibrating up and down. So over and over again, the original wobble that you created made the water beside it wobble. That made the water beside that wobble. That made the water beside that wobble. So we get this domino effect or chain reaction of your initial input of energy, your initial vibration, creating another vibration, which created another vibration, which created another vibration. That's what a wave is. We've got this medium that's elastic, Medium is the water. In this case, medium just means the material. You've put a disturbance in one place. That just means energy. You tapped it with energy out of your body. And that initial disturbance or that initial vibration triggers other vibrations. So even though you put the energy or the disturbance was in one position, eventually the energy from that initial disturbance travels all the way across the medium. A fancy physics word for travel is propagate. So kind of rehashing it, in our activity, the water is the medium. When you tap it, you're disturbing it, you're adding the energy, creating an initial vibration. That initial vibration, that triggers the other vibrations, which allows energy to travel or propagate across the medium. If we had fancy camera work and could film it differently or better, let's say, the water's vibrating up and down at a particular frequency. That depends on how quickly you were tapping it, and a particular amplitude. That depends on how hard you're tapping it. Also, the energy is rippling or going across the water at some particular speed. It started at one end of your little body of water. So many seconds later, or fractions of a second later, it ended up at the other end. It did a particular distance in a particular time, so we could do like a d over t to figure out the speed that the energy worked at. When you did the Slinky Lab, I asked you to observe the speed of those pulses as they traveled down the Slinky or the wire in the FET simulation, that kind of speed as well. All right, the investigation now is just going to flush out kind of things I've already said. What happens if you tap the water harder than you did before? If you tap harder, I've already said the answer out loud, but give it a try. If you tap harder, does it have an effect on the frequency, the amplitude, or the speed? The answer is when you tap harder, you should see a larger amplitude because you put more energy into it. If you tap harder, and that's all you do is tap harder, then you should see the same frequency because frequency is related to the physical properties of the medium. If you tap harder, you should see the same speed because speed is also related to the medium. Kind of connected to that, setting up what we're going to do soon. We're going to start talking about sound waves. The speed of a wave is connected to a medium, not connected to the frequency. So if we have a speaker playing some music, the energy from the speaker, those sound waves, are going to travel from the speaker to your ear. Your ear, eventually your brain decodes them, but the speed doesn't depend on frequency. So that means the high notes of the music travel at the same speed as the low notes of the music. The loud parts of the music, the higher amplitude, travel at the same speed as the quiet parts. The only thing that affects the speed is the medium, not the actual properties of the wave. A high note will travel the same speed as a low note, and a loud sound will travel the same speed as a quiet sound. Sound waves always travel at the speed of sound. It doesn't matter what frequency or amplitude of the sound. If for some reason you needed sound to travel faster, the only way that you can change the speed of sound is to change the medium, which for us is air. We're going to get to it in a lesson or two, but sound travels faster in hot air than cold air. If I was really desperate to get a sound to travel as fast as possible, I'd want to make the air as warm as possible. It wouldn't matter if I did high pitch, low pitch, loud or quiet, or some combination of that. The only way we can change the speed of a wave is to change the medium. When we start talking about sound, we would change the medium by changing the temperature of the air. There's a summary of all that. All right. This part's going to get a little messy when you try it, but what I'd like you to do is repeatedly tap your water over and over again every second. So kind of like a metronome every second. That's actually probably a little bit fast. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi. Tap it once a second and watch what happens to your waves. The disclaimer here is we're not ready for the second part. Once they hit the edge, they're going to start to overlap and interfere, and they do something we call interference. I don't want to bring that up quite yet. So just what do the waves look like as they're traveling to the edge before they start to reflect and bounce on each other? Now do the same thing, but tap twice as fast. How do the water waves look before they get into that messy interference when you tap the water more frequently? Try it, tap the water slowly, what do the waves look like? Then tap the water faster, what do the waves look like? All right, here's the answer. If we had a fancy camera and could take a picture of like the side of the water waves, when you're tapping kind of slowly, they would have this kind of wave shape. If you've done grade 11 math, sometimes we call it sinusoidal, like a trig function, it would have that over and over again. If that's what the wave looked like when you're tapping the water slowly, when you tap the water quickly, that's the change you should see. They would be kind of squished together more. When you increase the frequency, the higher frequency, that's this one, the spacing of the wave got much shorter. So here's a little bit more physics. When we're doing this kind of wave, the part that's kind of above its preferred spot we call the crest of a wave. The part that's below we call the trough of a wave. We already talked about amplitude. Amplitude could be measured up or down, but how far from that middle point to the very, very bottom of a wave, or it could be from the middle to the top of the wave. Those are both amplitudes. And our new word, if we measure the length of a crest, the start of a crest all the way to the end of a trough, so this distance down here all the way to there, we're going to call that a wavelength. It's down there all the way to down there. The exact same distance would be the top of a crest to the top of a crest, or the start of a crest all the way to the end of the trough. All those distances that I labeled in red, those are all exactly the same, and those are what we would call the wavelength of our wave. All right, notation-wise, wavelength is a distance, so its units will be in meters. It's a length, so the smart choice would be to call it capital L, but they wanted a special L since this is a special length. So I'm not sure why. I wasn't around. I'm not that old. I'm old, but I'm not that old. But for wavelength, they chose to use the Greek letter L. I'm going to call that lambda, and we're going to type it or draw it like that. When I write it, it looks like that. So what we saw before, what we talked about before is amplitude. That's how tall or deep a wave is. Amplitude is related to energy. If it's a sound wave, we hear amplitude as volume. Frequency is how quickly the energy, or sorry, the particle, the medium, is vibrating or wobbling back and forth. It's got the funny units of hertz, and we hear frequency as the pitch. A high frequency is a high sound, a low frequency is a low sound. Wave speed is how quickly the energy crosses the medium. How quickly did that water wave get from one end of your pool to the other end of your pool? That's the wave speed. Because it's just a regular speed, we're going to call it V for speed, and it's going to be a D over T kind of thing. Now the new, and wave speed, the only way we can change the speed of the wave is to change a medium. If I wanted sound waves to get to you faster, maybe there's some sort of emergency, it's not like I could send a high pitch and a high pitch goes faster. High pitch goes the same speed as a low pitch. To change the speed of a wave, you have to change the medium. And now the new one, this thing called wavelength. Wavelength is literally the length of one wave. So it's crest to crest, trough to trough, the start of one to the start of the other, the whole full wave. That's what a wavelength is. Because it's kind of a special distance, we give it the short form of Greek letter L or lambda, or type that way. Now, actually, you know what? We're going to hold off there. I'm going to start a new video on the math. Frequency is how high or low the sound is. Amplitude is how loud the sound is. Wave speed depends on the medium, and now we've got this new thing, wavelength. There is a connection between frequency and wavelength. So I'm going to pause here because the next part's got some math, a little proof, and I'll show you the connection between frequency and wavelength.